Don't say anything.
Sucks.
Math. Okay.
Looks like I can't do anything.
So today we're going to talk about SUSY. Does everybody know what SUSY is?
No.
Yes. Do you know what SUSY is? SUSY is supersymmetry.
Where did the Z come?
It's SUSY.
Oh, yeah.
Not SUSY. But anyway. Unfortunately, supersymmetry, so there's quite a few things that I could preface this with. It's a reasonably old idea in that it was put forth in its infancy, like in the late 60s, and it's been around ever since. It is an extremely deep subject, and it also has not been experimentally verified. And those three things conspire to make the literature on SUSY bewildering. There's a lot of it, there's a lot of research in it, there's a lot of results, there's a lot of notation, there's a lot of lingo. And so it's actually just like an enormous subject, even though it is literally just like a single kind of transformation that you're studying. And moreover, for a reason that we'll get to in a bit, the nature of supersymmetry makes it so that it's really, really hard to give people an intuitive, sort of concrete way of understanding it. And it's largely because of the fact that it deals intrinsically with spinors. And we all know that spinors are the least intuitive thing in all of physics. So unfortunately, like in contrast to the past few things I've talked about where I've been able to draw lots of nice pictures and give you things that kind of feel good and make sense, there is absolutely none of that in supersymmetry. I apologize. But as usual, I will do my best to mix in some technical details along with my best efforts to give you some sort of interpretation of what's going on. Although at the very end I will draw a nice picture, but it won't actually be directly related to supersymmetry. So if you're not aware, those in my class are, the standard model of particle physics, and this is our best understanding of fundamental physics to date, is based on the following sets of symmetries. So we have a set of space-time symmetries, and since the standard model is formulated on flat four-dimensional space-time, that's Minkowski space, this is the space of special relativity, then there is a set of symmetry transformations that take the form of space-time translations. That is, I can move in x, I can move in y, I can move in z, and then I can move in t. Those are just translations. And then these are combined, actually, technically in a semi-direct product with the set of Lorentz transformations. The set of Lorentz transformations include rotations in spatial planes, but then also boosts, changing your velocity along a particular axis. So altogether, this set of 10 transformations, 6 here, 4 here, correspond to what's called the Poincare group. And any Lagrangian that we write down for the standard model should be invariant under these space-time transformations. And one way we know how to do that is to work in terms of tensors or spinors, and just make sure that the Lagrangian is constructed out of overall invariance under these transformations. Now, less familiar, and you've seen examples of rotations, you know, even as far back as probably physics 2, maybe physics 1, certainly in your calculus class. So you've had experience with this set of transformations, maybe not in this fancy schmancy language, but another type of transformation that's very important in the standard model, which, believe it or not, you've actually dealt with as early as physics 2, are the internal transformations that do not have anything to do with space-time, but rather they're acting on the fields or the particle-like degrees of freedom, and they're analogous to these kinds of rotations in space-time, but they're more gooder thought to be more appropriately thought of as rotations in an internal vector space, something we might call an isospace. And As such, they don't necessarily have to have the properties of the Poincare group, like that these are real transformations and so forth. And so for the standard model, it turns out that there's a set of transformations that are actually all represented by complex matrices that satisfy certain conditions. It's not that important. But what's beautiful about this set of transformations is that forcing the Lagrangian to be invariant under these transformations is actually the source of the interactions in the standard model. And so we can identify the SU3 part as the strong interactions, or also what's called quantum chromodynamics. And then this funny looking SU to the left across U1Y, where Y is the hypercharge, is the unified electroweak interaction. And then, as people in particle physics are aware, at room temperature, this is actually broken. And so the symmetry group that we explicitly observe is the strong interactions, and then the U1 that corresponds to electromagnetism. So when I say you've seen this before, in your physics 2 class, you should have, if you wrote down an electric potential, realized that you could add a constant to the electric potential and it doesn't change the E and B fields. That's exactly this symmetry transformation. Okay? And also you can add a contribution to the vector potential and it doesn't change the magnetic field. Okay, and then this step of breaking this is the spontaneous symmetry breaking with the Higgs mechanism, which my particle physics class just learned all about. Okay? So now all of these are realized in terms of Lie algebras. So if we talk about a set of transformations, it's useful to think of them in terms of Lie algebras. These do form continuous sets of transformations. So any of these things that I'm talking about, you can start with the identity, the do-nothing transformations, like I don't do anything, and then you can do a very tiny transformation, and then another tiny, and by a successive compounding of tiny transformations, you can build up to anything you want. So you could like do a no rotation, and then you could do like an epsilon rotation around the x-axis, and then by doing lots of epsilon rotations, you can get to a 45-degree rotation around the x-axis. So those types of sets of transformations correspond to Lie algebras, and it turns out that the algebras are a nice and concise way of characterizing the transformations. And so in particular, if we look at the semi-direct product of space-time transformations, they have a Lie algebra that's given by the following set of commutators. P nu is 0, m mu nu, p nu is I, eta mu nu, p, nope, that should be a rho. Rho mu, and then m mu nu, m rho, we'll call it sigma. And this is just some nasty, I'll just write down one term and quit writing because there's like 6 of them. Where the rest of these terms are just permutations of the indices on the eta and the m. Okay, so what am I talking about here? Well, these are momenta. These are space-time momenta. Okay, they have this funny index mu nu because we're in space-time. So mu and nu and rho and sigma and everything, they take values 0, 1, 2, 3, where 0 corresponds to time, and then 1, 2, 3 is like x, y, z. And the momenta are the conserved quantities associated with translational invariance, but they are in fact the generators of translations. And it's the generators of the transformations which satisfy the Lie algebras. The n mu nu are tensors which generate the Lorentz transformations, so they're responsible for these SO13s. You can kind of think of this as a rotation matrix has 2 indices that act on like a vector index to rotate it. You know, like you do a rotation of a vector with a matrix. So this has 2 indices and this has 1. And that's why the Lorentz transformations have 2 indices. And by the way, for those of you who don't know what these square brackets mean, these are commutators. So if I write this, I'm really just talking about AB minus BA, which of course would be 0 if A and B could be switched, but you're not always guaranteed that, especially with matrices. So if I take a Lorentz generator and commute it with a momentum, then I get momenta out of it. The etas are just the metric of Minkowski space. And if I take two Lorentz generators and I take their commutator, I get back a linear combination of Lorentz generators. This would only include the m's. Okay? The details of this are not that important. For those taking particle physics, some of this should be familiar. For the rest of you, you'd be like, square brackets, cool. Don't worry, we're going to do curly brackets in a minute. Okay, also for the internal groups, we also have the algebras. And these are a little bit shorter to write because we just use a compact notation. So for SU3, if we take the commutator of two of its generators, then we just get a linear combination of the other generators. And by the way, this has 8 generators. So if I take the commutator of 2, then I generally get a linear combination of all the generators where these coefficients f are called the structure constants of the Lie algebra. And then the Lie algebra of SU2 can be similarly written, but in this particular case, the structure constants are the familiar Levi-Civita symbol, epsilon ijk, which is something that we actually encountered in our discussions of differential forms. That's that thing that's totally antisymmetric under the exchange of indices. And then Ariel will remind us what the Lie algebra of U1 looks like.
0.
It's 0, right, because there's only one generator. There's one generator, it has to commute with itself. Things commute with themselves, at very least. How many generators were there in here, Caroline?
3.
3?
Yeah.
Good. Okay. So we have 1 photon, we have 3 weak bosons, and we have 8 gluons. Okay, so that's like a super cursory reminder of things that you kind of learn as you study the standard model, and in particular its symmetry. Now, this whole story of the standard model wasn't even sort of finalized until the mid-70s. But years before that, people were actually trying to toy around with the idea of could we somehow combine space-time and internal symmetries. And what do I mean by combine space-time and internal symmetries? Well, if I wrote out the actual standard model group in full, it would look something like this. It would be translations, semi-direct product with the Lorentz transformations, direct product with the SU3, direct product with the SU2 left cross U1y. And, yeah.
Sorry, yeah, what is the IR 1,3? Or
Sorry.
That's R.
Yeah, that's R. These are the isometries of Minkowski space, or sorry, they're the translations in space-time, time and space. Okay, so to combine them, let's first of all let's think about what we would do, what we would find if we took, say, a generator from this set, maybe P mu, and a generator from this set. Just pick a G, any G, it doesn't matter. Okay. The fact that the space-time transformations are in a direct product with all of the internal ones means that this commutator is 0. And it doesn't matter if I pick a momentum or if I pick a Lorentz transformation generator. If I pick any G here, the commutators are going to be 0. Okay? This means that essentially the space-time transformations are completely disconnected from the internal transformations. If we wanted them to be connected in some way, then we would be looking for at least one of these commutators to not be 0. At least one of them. Okay, so generally speaking, when things don't commute, they're connected to each other in a non-trivial way. If they do commute, they're often completely disconnected. And there's a sense in which this is borne out in the case of translations and rotations. So if I rotate in X and I rotate in Y, the commutator is 0 because if I move a distance in X and then I move a distance in Y, I get to a point there. But if I instead first move the distance in Y and then move the distance in X, I get to the same point. The motion in X and the motion in Y are completely decoupled. I can do them in any order. It doesn't really matter. However, what we know is if I do a rotation in X and a rotation in Y, the commutator is not 0. And the way we can see that is we can take an object and we can rotate it around the x-axis a certain amount, say 45 degrees. Actually, let's say like 36 degrees, 45 could be dangerously degenerate. Rotate it around x by 36 degrees, rotate it around y by 28 degrees. And if I take the same object and do those in reverse order, it'll actually end up looking different. And that's because rotations in x and y are actually linked, and we know secretly why, because this is really a rotation in the yz plane, and this is really a rotation in the zx plane, and they both share z. Yeah?
So what exactly do you mean by a direct product between spaces? Is that?
Well, in this context, I just literally mean this absolute commutativity between any two elements of the spaces. So you could, in a sense, set up a vector space in which all of the operators here are acting, and then the total vector space would be a tensor product of space-time with that vector space with no operators that are actually acting non-trivially in both spaces. And so, if you wanted to write like a mega matrix that acts on this whole thing, because like this is a 3-dimensional, 2-dimensional, 1-dimensional, so that's a 6-dimensional internal space, this is 4-dimensional space-time. You could write this thing as like this big 10-dimensional matrix, but then you've got this funny non-homogeneous part, so you actually have to bump this up to 11 dimensions to actually encode the translations in terms of some linear operator. You could write a big-ass 11-dimensional matrix, but it would be block diagonal. So that's another reflection of it. Okay, any questions? That's probably the best answer I've ever given to a question. Anyway, all right, so usually I flip and I flop and I struggle. You Facebooking?
No, I'm not, sorry.
Lucky story. Okay, so, are you texting him?
What? No.
Anyway, all right, so I don't care, you can kind of do this isn't physics 1, you can just ignore me. Okay, so,
Yeah, I'll put it away.
I'm just
Is
kidding.
it comforting?
Okay. So, let me see where I was. Oh, yeah. I'm down here. Yes. Okay. All right. So people started playing around with this, trying to get this to happen, and then these couple really smart fellows, Sidney Coleman and somebody named Mandula, I can't remember his first name, came along and they're like, no. So Coleman and Mandula came out with what is in the physics literature often called a no-go theorem, which is basically saying, stop trying to do this, it's not going to work. We can prove on very general principles that what you're doing is fruitless. Okay, so no-go theorems kind of suck, but anyway, we'll get to that in a second. So what Coleman and Mandula did was they did the following. They said, let's just consider the scattering of two particles, A and B. So two particles are like flying through space. They kind of get near enough to each other to interact. And so there's some interaction. Maybe they're attracted to each other or they're repelled from each other. In this context, it's not quite as simple as that. That's the way we think of it with like charged particles or even gravitational interactions, but it's more subtle here. But nonetheless, we have two particles which are initially way far apart, and then they kind of get near each other. They could do something, and then at the end they go way far apart again. So this is my proxy for infinitely far apart. And this too is infinitely far apart, and this is something interesting happening in between. And so there's a very technical proof of this, but the spirit of it goes something like this. So what they said was, if you analyze this process, not even knowing what's going on with the interaction, you can use kinematics to constrain this. And in particular, from conservation of energy, momentum, and angular momentum, which we all know from physics 1, as long as you define your system to include everything, all of these things are conserved. They don't change with time. You can show that everything about these final two particles is completely determined. Their velocities, their energies, except for everything is determined except for theta, where theta is what we call the scattering angle. It's the final angle of departure of the two things. Okay? Now, the thing is, conservation of things like energy momentum and angular momentum arises because there are symmetries in the theory associated with translations in space, translations in time, rotations. So conserved quantities come from invariances, symmetries. All right? Well, what we're trying to do if we have the internal symmetries in bed with space-time symmetries is we're basically trying to take this list and add another conserved quantity. And what Coleman-Mandula figured out, and it's a relatively straightforward exercise in four-vector gymnastics, is that if you add any other conserved quantity that has a space-time effect, this is having an effect in space-time, then you actually sort of over-constrain theta. If you analyze it, you actually discover that theta can only take discrete values. So before, theta could take a continuum range of values. Okay, it's completely, there's a limit on what values any angle can take. But now, instead of being a continuum of values, it's just set of discrete values of the angle. Okay? The problem is that one of the assumptions in doing these calculations is that the final answer for the amplitude, that's how likely any given outcome is, should be an analytic function of the scattering angle. Okay? But this is a contradiction. You can't be an analytic function of the scattering angle if the scattering angles are only allowed to take a discrete set of values. Because an analytic function is essentially a continuous function. But it's kind of like saying I've got a function of x, but x can only take discrete values. There's no way that's going to be an analytic function. Yeah?
So why can't you throw away the analytic part of it and just use like quantized scattering angle?
You could, but that would fly in the face of observation.
Okay.
So this is really and truthfully rooted very deeply in all of the abstraction of particle physics. This is actually what we observe. We take particles that are very far apart, we slam them together, and then we measure what comes out the other end. So we measure all the outcomes, and we find that, generally speaking, the probabilities associated with outcomes are analytic functions of the scattering angle. So you could dispense with it, but then you're departure from reality. So trying to maintain this sort of observable consequence, we find we have a problem, unless, of course, theta is just constrained to be 0. But if theta is 0, then there's no scattering happening. Okay, so the function is actually just 0. So what Coleman-Mandula proved was if you have too much space-time symmetry, then things don't interact. But of course, that's not a very interesting theory. Okay, so you sort of over-constrained the theory to the point where you don't have the freedom for interesting things to happen. Now, what's important in this is that this no-go theorem, like many great no-go theorems, are based on a set of assumptions. You have to start from something. I'm going to assume, analyticity of this this is called the S matrix, or the scattering amplitude. Analyticity of the scattering amplitude, I'm going to assume there's a couple of other technical things, but among them, one of the important ones is that the symmetries in question are based on commutators. Okay? Which, of course, all the symmetries that we're talking about, that we've written down, are based on commutators. Another way to think about that is that the symmetries are bosonic. So the Coleman-Mandula theorem assumes bosonic symmetries. So let me explain for a minute what that means. So a bosonic symmetry is a symmetry where, first of all, the generators satisfy some Lie algebra conditions given by commutators. And one way to kind of associate this with the word boson, which you might be familiar with from any level of quantum mechanics, is in terms of if I take two bosonic operators that create excitation, so these would be like bosonic creation operators in some field, and I act on some vacuum state, then this is generally not zero. Okay, I can create two bosonic excitations of the vacuum successfully. Okay, now this is consistent with the commutator relations, because if I take the commutator of a bosonic operator with itself, that is automatically zero. Okay, because this is just something minus itself. Okay? However, this opens up a loophole to the Coleman-Mandula theorem. And that loophole is that we could, instead of bosonic transformations, consider fermionic transformations. That is, we could consider transformations which satisfy a Clifford algebra instead of a Lie algebra. So a Clifford algebra is something which involves an anti-commutator. And so if I have, for example, a fermionic creation operator and I take the anti-commutator with itself, this is AF plus AF. Okay? And if my Clifford algebra is such that the anti-commutator of AF with itself vanishes, now this is just a stipulation, but if that were the case, then this Clifford algebra imposes that AF is zero. Because if AF squared plus AF squared is zero, then AF is equal to minus AF squared. Or AF squared is equal to minus AF squared. Something can't be equal to negative itself unless it's zero. That's not a problem here. Okay? This can be non-zero and be consistent with this because this is something minus itself, which we already know is zero. But because this is something plus itself being zero, that implies that this thing squared is zero. Okay? But what that means is that for this Clifford algebra, if I try and make two fermionic excitations of the vacuum, I have to get what? Zero. What do we call that?
Conservation of fermion numbers.
It's the Pauli exclusion principle. It is the statement that you cannot put two spin-a-half particles in the exact same state. Because if you try to do that, you'll get zero. That's what this is trying to do. It's trying to create two spin-a-half particles in an identical state, and it can't happen by the Pauli exclusion principle. You can put as many bosons as you want in the same state. It's perfectly consistent. So that's what I mean by bosonic and fermionic symmetries. The words boson and fermions correspond to the statistics, which is tied to this idea of, really it's what's the symmetry under exchange of wave functions, but it can be tied back to this statement by Pauli that you can't put two electrons in the same box.
But so AF on phi is not zero.
No. AF on phi is not zero, because you can create a fermion in a state. It's when you try and stick another fermion in the same state. This could be a different fermion operator. That'd be fine. You just create two fermions in different states. Yeah. Okay. Okay, so if we allow ourselves in trying to combine space-time and internal symmetries, the possibility of anti-commutator relations, then it turns out that we can evade this no-go theorem. And so what we are then left with is a new algebra, and we're really only concerned with the space-time part. where I have the original algebra between the bosonic generators, but now I add in some additional elements. So I'm going to call these new things Q alphas. So the Q alphas are the fermionic transformation generators. So they're for these new transformations, they're the analogs of momenta as generators of translations, and the n mu nus as the Lorentz generators as generators of Lorentz transformations. So these new Q alphas, first of all, they will actually commute with momenta, okay? But when I'm talking about a Q alpha and another Q, in particular, if I talk about one Q alpha and one Q beta, their anti-commutator vanishes. But if I take the anti-commutator of Q alpha with, and I apologize, but there's no good way to do this, with a Q bar beta dot, then this is actually something non-trivial. And it's given by that. Okay, so spinor notation sucks. And unfortunately, in particle physics, we just avoid indexing spinors and spinor operators. We're just like, we're not even going to bother. We're just going to write things as matrices and let order of operation follow from that. But in supersymmetry, you really have to. So what's going on here is P mu is a vector in space-time. So it's got this mu index that tells me, am I looking at the time, the x, the y, or the z components. Q is a spinor. So the alpha is an index where, Wolfgang?
In the spin space.
In spin space. And spin space is not the same as space-time, though it's related to it. This in 4 dimensions takes how many values?
4.
4. If you have a Dirac spinor in 4 dimensions, it actually takes 4 values, just like that. Now here I'm taking the anti-commutator between different components of the same spinor. Here, I'm taking the anti-commutator between a spinor and its Dirac adjoint. Okay? Don't worry, you know, what Dirac adjoint means. It's just you take this spinor written as a vector and you do some shit to it, and then you get another one, and we call that the Dirac adjoint. And it's got some really nice properties. But this, by the way, is analogous to something like this. Writing the momentum with a lower index and writing it with an upper index, calling one covariant, calling one contravariant, calling one a vector, calling one a dual vector. This is just the spinor language of the same thing. But what we observed is that this is where the love happens, right? Because up to this point, the Q's are completely disconnected from space-time. But here we notice 2 Q's give a P. So there's something non-trivial connecting this new transformation and transformations in space-time. Okay. Caroline, you got all that?
Every word.
Every word. Okay, awesome, sweet. So happy. Okay. Good. All right, no, I'm kidding. It's like, I was writing these and I was just like, I feel so sorry for these students.
Hey Caroline, do you want to come sit back here, dude?
Yeah. Selected my seat better.
Comfort each other. Yeah, there's a seat back there. You can be
I tried to.
up in my business.
I'm not surprised.
There's literally like 10 minutes left.
I'm here though.
There's so many questions.
Okay, well, there.
There's no
That's where we
longer a
are,
seat back
Spencer.
All that? What?
We're there. You got that?
Yeah.
Okay. All right. And by the way, folks, that is not the time derivative of beta. If you think that's the time derivative of beta, you probably ought to think about leaving. It's called a dotted index, and it's just a way to distinguish the indices of the Dirac adjoints from the indices of the original. It's kind of like up and down being different for vectors and dual vectors. Okay. All right. Now, yeah. So Coleman-Mandula, cuckoo on you. We found a way to get around you. Now, I have to say, though, that the Coleman-Mandula theorem is not lost, because what we discover is that, given the Coleman-Mandula theorem, this is really the only way to extend the group of space-time symmetries to be wrapped up with something else. okay? Because any other thing you try is going to be ruled out by the Coleman-Mandula theorem. So there's a uniqueness to this extension. You can only add in another transformation that corresponds to a fermionic transformation. Okay? All right, so now, there are some really interesting consequences of the fact that these new transformations are generated by spinors instead of the more familiar tensors that we see in space-time transformations. So one of them is that we know from the spin statistics theorem that a boson is an integer spin particle, and a fermion is a particle with some half integer spin. Okay, the simplest case is that the electron, which is a fermion, and it's probably the most famous fermion from quantum mechanics, the Pauli exclusion principle, you can't put two electrons in the exact same energy state, hydrogen atom, blah, 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 blah. The electron has spin a half. Okay. For bosons, you're probably not too familiar with bosons, but the photon is actually a spin 1 boson. The Higgs is a spin 0 boson. Okay. And for bosons, you can cram as many of them as you want into the same quantum state. But what that means is that the M's and the P's are integer spin, and in fact, you can actually count the spin by the number of indices. So the P's carry their spin 1, and you can also, well, I'll get into that. And the M's carry 2 indices, and they actually correspond to spin 2 transformations. And the Q's, they carry 1 spinor index, so they actually correspond to a spin a half. Okay. Now, why that's important is because when we do a space-time transformation, say we take a vector and we transform it to some new vector by the application of Lorentz transformation. Okay. Okay. The fact that we start with a vector, or we start with a vector here, and then after this transformation we get back another vector, is tied to the fact that this transformation is built out of these M's. And so for those of you who remember, an arbitrary element of a Lie group is built with the exponential map, with a vector of generators. Sorry. Combined with a vector of parameters. And so the M's would go here, and then after you do this exponentiation, you would end up getting the lambdas. But the point is just that the lambdas are built out of the M's. And it's because the M's are tensorial and they have the correct upper and lower indices, that the lambdas can kind of take a vector and give me back another vector. Okay? So the idea is that I have a spin 1, and after this transformation, I get back a spin 1. Okay? Now, what's maybe not obvious is that I can do the same thing with a spinor, because we know that if I do like a Lorentz transformation of a spinor, then I take the spin representation of the Lorentz transformation, act on the spinor. And so what I have here is I have a spin a half, I have some integer, some sort of tensorial transformation, and that's going to give me back something which is half integer spin. Okay? So there's a sort of an angular momentum thing that you probably remember from quantum mechanics, this angular momentum addition, that goes something like this. If I start with an integer spin and I combine it with another integer spin, I'm going to get an integer spin. And by the way, I don't even have to say the words spin here. These correspond to numbers as well. And if I start with an integer spin, or sorry, if I start with a half integer spin, and I somehow combine that with an integer spin, then I have to get back a half integer spin. Okay, so like I could take two spin 1 particles And it's actually a more interesting thing than just the arithmetic, because I could take two spin 1s, and I could get back a spin 2, or I could get back a spin 0. But I could never get back a spin 1/2. If I start with a spin 1/2 and maybe a spin 1, then I could get back 3/2 or 1/2. Okay? You can basically subtract off the z component of the spin 1/2 and go from 1 to minus, or from, you could do 1 minus 1/2 and get a 1/2. But the point of this is that now, from these supersymmetry transformations, I have the following. If I start with an integer spin, and I do a SUSY transformation, which is built out of these Q's, which are spinners, then I'm actually acting with a half integer spin transformation. And so then what must I get after the transformation? Something with half integer spin. Likewise, if I start with something with half integer spin and I do a half integer spin transformation, I must get something with integer spin. So this is the origin in this story of the more simple way of talking about supersymmetry, which is that it exchanges bosons and fermions. That's a weird thing. No other transformation that we do, in the standard model at least, does this. If we do a gauge transformation, like a rotation in color space, or if we do an electromagnetic gauge transformation, or a weak doublet transformation, if we act on spinners, we always get back spinners. If we act on bosons, we always get back bosons. Okay. Here, though, it's saying if I act on a boson, I'm going to get back a fermion, and vice versa. Okay? So there's something very strange and different about this transformation compared to how we have seen this in, or how this story has kind of played out with other transformations. Now, by the way, you can play around with this identification, but you can also just sort of straight up see this from the indices, because if I start with a vector and I act with a supersymmetry transformation, so there's going to be some function of this, but I'll just write it like that, then the combination is going to be some object with both a spinner and a vector index. But this is actually the way we would notate a spin 3/2 object. Okay, so the fact that you're just throwing on a spinner index is telling you, hey, you're getting some spin 1/2 behavior out of this. Okay, so, been horrible as usual. Okay, I am going to, say the following, and I'll skip this. No, screw it. I'll just do it. All right, so here we go. If you wanted to, I'm in that case again. I always find myself here. Okay, so this guy right here has some very interesting consequences, which I'm not going to spend a lot of time on. But first of all, you can ask yourself, if I do a supersymmetry transformation, do I actually have to transform everything? So for example, if we do an electromagnetic gauge transformation, we don't do anything to neutrinos. Why?
No charge.
Because they don't have electric charge. A transformation only affects things if they carry charge under that transformation. Okay? So we could ask, when I do a supersymmetry transformation, do I have to transform everything, or can I just transform a small handful of things? Okay? Well, unfortunately, this expression tells us, no, we have to transform everything. Because supersymmetry transformations are tied to translations. But if you do a translation, everything gets affected. Translations are kind of in bed with the ideas of energy and momentum. And you do something in space-time, everything gets affected, nothing escapes it. So the fact that everything feels this immediately implies that everything must transform under supersymmetry. Okay? So this thing tells us A, SUSY is in bed with everyone. Okay, there's no slut shaming in here, but SUSY's in bed with everyone. Okay. Another thing that we could ask is if I gauge SUSY, see how SUSY measures up, then what I'm really doing is I'm saying I want to let this transformation be local. So this is what we do to the global symmetries of the standard model Lagrangian in order to create the interactions. We make the symmetry transformations local. Okay? But you'll notice if I gauge supersymmetry by this relationship, I must gauge translations. But a theory of gauged translations is general relativity. So gauging supersymmetry automatically incorporates gravity in the form of supersymmetry, or in the form of general relativity, and the resulting theory is what we call supergravity. Okay, so again, these consequences follow from this fact that the spinor transformations are in bed with momentum. So if you try and do something here, it affects this, or the fact that momentum affects everything tells us that this has to affect everything. Now, if we did try to create a supersymmetric Lagrangian, just to write down a really, really quick and dirty possibility, so I could take the Klein-Gordon Lagrangian for a complex scalar field, and I could add to it the Dirac Lagrangian. Okay. The first thing we know is if I'm going to do a transformation which changes phi into a fermion, well, the phi must turn into the psi. So the supersymmetry must be taking phi and sending it to psi, but at the same time taking psi and sending it to phi. Because if it's a symmetry, this thing must look the same after I do the transformation. Now, it's not this simple, obviously. There's only one derivative here. There's a quadratic in derivatives. There's this gamma mu. The actual transformation that you do is a little more complicated, and I've written it down in the notes. But at any rate, if you do the correct supersymmetry transformation on this Lagrangian, you'll find that you get back exactly the same expression plus a total derivative. But if you've got a Lagrangian, adding a total derivative to it will not change the equations of motion. So it's the same physics. Okay? But here's the important consequence of that. In order to have supersymmetry be a symmetry of a Lagrangian, every phi has to have a partner psi. Moreover, the masses of them have to be the same. In fact, all of the quantum numbers have to be the same. Now that creates a problem, because that means if we had a supersymmetric theory, the electron would have to have a bosonic counterpart that had the same mass as the electron, the same charge as the electron. Okay? Except it would be spin 0 instead of spin 1/2. But we don't observe that in nature. We don't observe any of these superpartners in nature. Okay? Now, if we don't observe these superpartners in nature, does that mean that this symmetry cannot play a role in physics or in the standard model? Do we know of any other symmetries that we don't directly observe that are important symmetries in the standard model? Yeah, exactly. SU2 left across U1 hypercharge. That's an important part of building the standard model, but it's not what we observe. We observe the spontaneously broken form of that. So what we can infer is we do not experience supersymmetry as a manifest symmetry of particle physics, but there's no reason why it could not be spontaneously broken. And in fact, if it's spontaneously broken at the same time that the electroweak symmetry is broken, remember this uses the Higgs mechanism to give everything mass. You could at that point give masses to the superpartners that are so large they're beyond any experimental bounds. So this spin zero version of the electron could exist. It would just have such a large mass that we haven't encountered it in accelerators. Okay? Now, I've said all this, and I've given you no motivation for why any of this might be remotely useful. And there's actually three really amazing reasons. There's lots of reasons why this is useful, but I'll give you three quick ones. First of all, the lightest superpartner, okay, this is a supersymmetric particle. It's a pair to one of the standard model particles. The lightest one is stable. It cannot decay because to decay, it would have to turn into a standard model particle and then decay by the standard model interactions. But if the symmetry is broken, it can't turn into a normal standard model particle. If it's the lightest supersymmetric particle, none of the interactions in the supersymmetric particle part of the story can make it decay because it's the lightest thing. The lightest thing can't decay. Okay? But this is a very massive thing. Very massive stable particles don't really exist. Generally in particle physics, a very massive thing decays very quickly into lighter things. But here we have a possibility of a very massive stable particle, which is an excellent candidate for dark matter. Okay? So not just supersymmetry, but broken supersymmetry is a really nice possibility for solving the dark matter problem. Okay? Another two things that are really useful about supersymmetry, which unfortunately is going to require like a 30-second lesson in renormalization, is the following. So everybody's familiar from E&M with classical charge screening, right? So classical charge screening just says if I take a charge, maybe Q+, and I put it in a polar medium, so everything is little dipoles, then the minus ends of the dipoles will go towards Q, the pluses will go away, and so my medium will sort of align itself like that. Okay, and you can fill out a bunch of these. Okay, but what happens is, if I want to know what charge would I see if I were at this position, I would draw a Gaussian sphere at that radius. And if I wanted to compare the electric field I would sense there, I would compute that from the total enclosed charge. But as I get closer and closer, the spheres that I'm drawing are intersecting less of these pairs. The further out I go, they're intersecting more of the pairs. So what happens is, as I go further out, the total charge enclosed goes to, it becomes a smaller value because the minuses that you're including inside of the sphere are canceling off the positive charge that's seated there. Okay? If you wanted to actually see just this charge, you would have to basically go to r equals 0. You'd have to go right down to where that charge is. Okay? So what we can say is that Q effective changes with distance, but that also implies that it changes with energy, because to get closer means you have to use more energy to probe it. Now, that's classical, but it turns out that in quantum field theory, the same effect happens, but this time, these are virtual electron-positron pairs. So these are all E plus E minus. These are popping in and out of the vacuum. So unlike this case where this might be like a crystal lattice of dipoles or something with some atomic separation, here there's no sense of separation. This is really just a continuous soup of these pairs. But the same effect happens. You get some kind of running. So what we discover is that in quantum field theory, couplings change, charges change with energy. Okay? Well, if we look at, and I'll just give you one example, but it's going to motivate what we're going to talk about next time. If I actually look at the three charges of the Standard Model, the strong color charge, the weak charge, and the electromagnetic charge, then what I find is that with increasing energy, the electromagnetic charge increases, the weak charge decreases, and the strong charge decreases. Okay? So this is E and M, this is weak, this is strong. Now one thing that we know is that this point right here is special. What's important about that point? Yes, that is where the electroweak unification happens. So this is electroweak unification. Okay? So really this picture should look more like this. Beyond this, there's something like that. Okay? But this is what you get if you just do the calculations with the Standard Model. If you do the calculations in the minimally supersymmetric Standard Model, you find the following result. The electromagnetic coupling increases, the weak coupling decreases, and the strong coupling decreases. And they meet at a point. And that point suggests that all three of those interactions are actually unified into a single grand unified interaction. So the presence of supersymmetry is one of the main motivations behind the idea that all of the Standard Model courses actually unify at some high energy scale, called the gut scale, and that's what we're going to talk about next time. Oh my God, how do I do this? I decide that 4 pages is too much, and then I come in with 5.